Hello and welcome to this lesson on exponential functions. So, exponential functions and properties of exponents. There are different definitions for an exponential function. For the purposes of this lesson, we will be using the following definition of an exponential function. So, definition: exponential function. An exponential function is a function that can be written in the following format. F of x is equal to a times b raised to the x exponent. So here are some examples. F of x is equal to 4 times 8 raised to the x exponent. Another example, f of x is equal to 8 raised to the x exponent. So we can have a coefficient in front, but we don't have to have a coefficient in front. We have f of x is equal to 2 raised to the 3x. We don't have to have just a variable. We could have a coefficient times a variable in the exponent. F of x is equal to 2 raised to the 3x plus 2, so we've got an algebraic expression in the exponent. And then my last example here is f of x is equal to 4 times 2 raised to the 3x. So what makes these exponential functions is an exponential function consists of a base number. Notice the base is a nice number, it's a constant, raised to an exponent that has a variable expression. So sometimes it's just a variable, sometimes it might be a variable and a coefficient, or it might be a more complicated variable expression. And then possibly having a coefficient in front. Since exponentials involve exponents, let's briefly review the properties of exponents. So, properties of exponents. This first property of exponents says a to the n times a to the m is equal to a to the n plus m. So an example usage, x to the third power times x to the fifth power, that's equal to x to the 3 plus 5, which gives me x to the 8th power. In calculus, and in this lesson, you could see this property used in the reverse. So let's consider the following example. 3 raised to the x plus 4. So here I've got it written as addition, and I'm going to break it up as two things that are multiplied where the base numbers are the same. So 3 to the x plus 4, that's the same thing as saying 3 to the x times 3 to the 4th power. And then when I do this, well, the 3 to the 4th power, that will simplify and give me an 81. So 3 to the x plus 4 gives me an 81 times 3 to the x. So in calculus, you might see this type of algebraic manipulation. When there is a constant term, a number term that is added or subtracted in the exponent, this property is used to rewrite the exponential as a coefficient and that base number raised to just a single term that has our variable term. Now I'm going to go back and take a look at a couple of the examples that we had earlier. So if we take a look at a couple of examples we had earlier for our exponential functions, this f of x is equal to 2 raised to the 3x plus 2. And this 4 times 2 raised to the 3x, these two are identical. They're equivalent. So if I broke this apart, this would be a 2 raised to the 3x times a 2 raised to the 2, and 2 raised to the 2 power would be an exponent of 4. All right, let's take a look at a couple more properties of exponents. So the next property of exponents says this. If I am dividing and the base numbers are the same, I have a to the nth power over a to the mth power, then I can subtract those exponents. So that would be a to the n minus m. So in example usage, this would be x to the third power over x to the 7th power. So that's going to equal x to the 3 minus 7. It's always the top exponent minus the bottom exponent. And then 3 minus 7 gives me an exponent of negative 4. My next property here, if I have a times b in parentheses, and that's raised to an exponent of n, then the a gets the exponent of n, and the b gets the exponent of n. So the example usage here is I have 2 times x raised to the 4th power. So that's going to be 2 to the 4th power times x to the 4th power, and the 2 to the 4th power simplifies to a 16. So that gives me a 16 x to the 4th. The next property here, I have a fraction raised to an exponent, a over n raised to an exponent. This is equal to a to the n over b to the n. And an example usage of this would be y over 5 raised to the exponent of 3. That's going to equal y to the 3rd over 5 to the 3rd, so they both get the exponent of 3, and that gives me y to the 3rd over 125. Now let's take a look at this next property. A to the n exponent raised to the m exponent. That is equal to a to the n times m. So an example usage, if I have x to the 3rd power raised to the 5th power, that's equal to x to the 3 times 5, which is 15. Or I could also have it written as x to the 3rd power raised to the x power. That's going to be a 3 times x, which is 2 to the 3x. This property can also be reversed. So let's consider this 2 to the 3x. This 2 to the 3x, since those are multiplied, I could rewrite this as a 2 to the 3rd raised to the x, and then the 2 to the 3rd power is the same thing as 8. So that would be 8 raised to the x exponent. And if you take a look at some of these examples that I had up here, notice the examples of my exponential functions. Here I have the 8 to the x, and I have a 2 raised to the 3x. Notice that those are examples. These two happen to be equivalent. Alright, so let's take a look at this next property. If I have something raised to a negative exponent, I can flip it, I can invert it, so a to the negative n is the same thing as 1 over a to the positive n. So an example usage would be x to the negative 4, that's equal to 1 over x to the 4th. In calculus, you might see this used in reverse, so consider the following examples. If I have 5 over x to the positive 2 exponent, I can flip that, and that becomes x to the negative 2 exponent. Or, if I have 2/3 raised to the x exponent, I can flip this fraction, and that becomes 3/2 raised to the negative x exponent. Alright, let's take a look at the graph of an exponential function. So if we have an exponential function that is in this format, f of x is equal to b times x, where that base number is larger than 1, then we're going to have a graph that looks like this. So looking at this graph, notice that this graph hits my y-axis at the point 0, 1, and I have a horizontal asymptote along the x-axis. So any exponential function that's in the format of b raised to the x exponent, where b is larger than 1, will look like this. Now, I said that the base number had to be larger than 1. If b is equal to 1, then I would have y equal to 1 to the x exponent. So if I start raising 1 to any exponent, 1 times 1, 1 times 1 times 1, 1 raised to any exponent is still 1, and we'll no longer have the exponential curve. So that's why we don't use a base number of 1. So now let's consider base numbers between 0 and 1. So if we have a base number between 0 and 1, we can rewrite the exponential function as the following. So if I have a 2/3 raised to the x, 2/3 is between 0 and 1, I can flip that fraction and change the sign of the exponent. So that's the property that we saw earlier. So if I have a base number that is less than 1, I'm going to flip it, and that base number is now greater than 1, and I change the sign of that exponent. Now notice that I don't have a base number of 0. If the base number happens to be 0, if I raise 0 to any exponent, 0 times 0 times 0, well, that's always 0. And I no longer have an exponential curve. And for this lesson, we will not consider negative values for the base number. Let's take a look at shifts of exponential functions. So, the following are modifications to the exponential function that will shift the function either up or down. So if I have f of x is equal to b to the x. Now this b is any number larger than 1. So that can be 2 to the x, 4 to the x, as long as it's larger than 1. So this is going to shift the exponential function up by 3. So it's going to take that basic curve, and it's going to move everything, including the horizontal asymptote, up by 3. If I have f of x is equal to b to the x minus 5, then that's going to shift my exponential function down by 5. The modifications that will shift my exponential function left and right are the following. If f of x is equal to b raised to the x plus 4, notice the plus 4 is inside of my exponent, whereas up here the plus 3 was not inside that exponent. So if the plus 4 is inside the exponent, this will shift my exponential function to the left by 4. And if I have f of x equal to b raised to the x minus 2, where the minus 2 is in the exponent, so a minus 2 in the exponent is going to shift my function, shift my graph to the right by 2. Now let's take a look at reflections. So the following modifications to an exponential function will reflect the function either across the x-axis or the y-axis. So if I have f of x is equal to b raised to the negative x, this will flip my function around the y-axis. If I have f of x equal to negative of b to the x, the negative's out in front rather than inside the exponent, that'll flip my function across the x-axis. Now let's take a look at some uses of the exponential function. So exponential functions can be used to describe mathematical models that involve percent growth or decay. So the function a is equal to b times 1 plus r raised to the n exponent, where b is the amount before the growth or the decay, a is the amount after growth or decay, n is the number of growths or decays that occur, and r is the growth or decay rate converted to a decimal. So if it is a growth, the r is a positive number. If it is a decay, then r is a negative number. So let's take a look at an example. So let's say the value of a YT 1300F light freighter decreases 5% every month after it is purchased. If Mr. Moore purchased a YT 1300F light freighter for 600 megacredits, what is its value after 36 months? So solving this, the amount before the decrease is 600 megacredits. I'm looking at 36 decrements, 36 months, and my rate is a negative 0.05. So plugging those numbers into our formula, this will give me a is equal to 600 times, open parentheses, 1 minus 0.05 raised to the 36 exponent. And using my calculator, that gives me a is going to be approximately 94.7 megacredits. Another use is compound interest. So this formula is a modification of the one above, and it's used for compound interest. So I have a is equal to p times, open parentheses, 1 plus r divided by n, raised to the n times t exponent, where a is the amount after interest, p is the amount before interest, n is the number of times interest is compounded in 1 year, excuse me, and t is the time in years. So let's take a look at an example of this. Example number 2. If Philip J. Fry has 93 cents in a bank account that makes 3% yearly interest compounded quarterly, how much will he have after 1,000 years? So here my P, that is 0.93. My R, so there's a typo there, that should be 0.93. R is 0.03. N, the number of times interest is compounded in 1 year, that's quarterly, so that's 4. And T is 1,000. So plugging these numbers into our formula, I get A is equal to 0.93 times 1 plus 0.03 divided by 4 raised to an exponent of 4 times 1,000. And here's how I keyed it into my calculator. I did 0.93 times, open parentheses, 1 plus 0.03 divided by 4, close parentheses, exponent, open parentheses, 4 times 1,000. And that calculated to, well, something like 8.86 times 10 to the 12th power. I actually wrote the number out, but that gives me about 8,885,915,952,000. Quite a bit of money. Now, many times we are interested in continuous growth or decay. The formula for continuous growth or decay is the following. A is equal to P times E to the R times T, where A is the amount of money after the growth or decay, P is the amount of before the growth or decay, R is the continuous growth rate or decay rate, and T is the time. And E is something called Euler's constant. It's a number like pi. It goes on forever and ever, and there's no repeating sequence to it. It's 2.71828. So let's take a look at an example of this. Left unchecked, the vampire population of Santa Clara would have a continuous growth rate of 30% per month. If the current vampire population is 20, how many vampires will there be in 12 months? So our solution, P is equal to 20, R is equal to 0.30, T is equal to 12. Plugging these numbers into our formula, I get A is equal to P times E to the R times T, which gives me 20 times E raised to the 0.30 times 12. Plugging this into my calculator, I do 20 times, and that E is located above a button that's labeled LN. So I'm going to do 20 times either my second button or my shift button, followed by my LN button, and that should put the E on the screen. And then I'm going to do open parentheses, 0.30 times 12, close parentheses, enter. And since we're talking about number of vampires, I rounded it to a whole number. So that's going to be 732 vampires. So the one bad thing about Santa Clara, it's all the vampires. So thank you for watching this lesson, and I hope to see you in the next lesson.